we wrap up Chapter 2 with a section that deals with various pairs of congruent angles. In Section 1.5, we introduced the concept of vertical angles. This was the definition. That definition describes the fact that vertical angles are on opposite sides when two lines cross, like angle 1 and angle 2. So that should be a review. And before I get to the theorem, I want to point out here that this definition only tells you how to identify vertical angles. It tells you nothing else about them. I will be coming back to that point again a few times. Now this picture is pretty simple. However, there will be times when the picture has a lot more going on. I have pointed this out before, but if you struggle seeing things when too many lines are involved, then highlighters or colored pencils are your friend. Here, if I want to identify which angle is vertical with angle 1, you can use them to color the lines that make up angle 1 like this. With those lines colored in, it becomes obvious which one is vertical with it. Angle 2 is vertical with angle 1. So the definition lets us identify a pair of vertical angles, but that's it. Let's work on what else we might be able to do with them. Here are a bunch of examples of vertical angles. I've even color-coded the pairs for you. Given all of these examples, you should be able to see what all these vertical angles have in common. What do you notice about each pair of vertical angles? It is most dramatic with the bottom left grouping of angle 9 and angle 11, as well as angle 10 and angle 12. You should be able to see that every pair is the same size. So in summary, we have this definition. The definition lets us identify vertical angles. The theorem allows us to say that the vertical angles are congruent. At this point, it should seem obvious that I'm really trying to hammer home the difference between the definition and the theorem. There's a reason. It is going to be very common to use vertical angles in a proof. So you might have a situation like this. The given, prove, and the rest of the proof are immaterial. I just want to focus on that second line. You want to say that angle 1 is congruent to angle 2, which is correct. It is. However, the reason is the problem. I have been hammering home the difference between the definition and the theorem because students constantly and repeatedly make this mistake. They put definition of vertical angles as the reason. That's not right. Don't do that. The definition only lets us identify them, nothing about them being congruent. You need to say the vertical angles theorem instead. That is what tells you they are congruent. I have really tried to impress upon you that difference, but I have just taught geometry long enough to know that this is an incredibly common mistake. Highlight it in your notes somehow. It's the theorem that says the vertical angles are congruent, not the definition. A quick note before we move on to the paragraph proof. This is the first theorem presented in the book, so let's take a quick look at the difference between a postulate and a theorem. In Chapter 1, we had the linear pair postulate. Like all postulates, it was a statement so basic, so simple, so obvious that we assume it to be true without proof. And now we have the vertical angles theorem. Theorems are usually a bit more complex than a postulate. With theorems, we no longer just accept that it is true on blind faith. With a theorem, the statement does have a proof behind it, demonstrating that it is true. So that's the difference between the two. There will be a lot of postulates and theorems in this class. The postulates are just assumed to be true. The theorems actually have a proof behind them. Next, we have a paragraph proof. This is a different style of doing a proof which shows up in this section. Last section we had this proof as an example, and it is a fine two-column proof. I will show you the equivalent proof as a paragraph proof. In general, paragraph proofs are exactly what they sound like, a proof in paragraph form. It reads more naturally, so some people like that, but they are often a little less organized and thus harder to follow, which makes the two-column proof more common. Paragraph proofs are generally more common on shorter proofs. In any case, here is the equivalent paragraph proof. You can pause here and read over it if you want. We will do a couple of paragraph proofs this year, but most of the proofs that we will do will be two-column proofs. The basic idea is to talk through your proof in a paragraph instead of the more rigid and organized two-column proof. Hopefully this next theorem makes a bit of sense. This is the official definition. It will make more sense if you see an example. Here's a picture where angle 1 and angle 3 are supplementary. In addition, angle 2 and angle 3 are supplementary. The theorem says that since angle 1 and angle 2 are both supplementary to angle 3, then angle 1 must be congruent to angle 2. This should make some sense. To give you more specifics, the measure of angle 3 is 123 degrees. Since it is 123 degrees, every angle supplementary to it must measure 57 degrees. If every angle supplementary to it must be 57 degrees, then every angle supplementary to it must be congruent to each other. Make sense? This works no matter what the measure of angle 3 is. Then we have the congruent complements theorem, which works just the same as the congruent supplements theorem, except we make one tiny change. Based on the name, you can probably guess the change. This was the congruent supplements theorem. This is the congruent complements theorem. In red, I've highlighted the change. Just change one word in the title and one word in the definition, and you are done. In practice, this works just like the congruent supplements theorem. And to give a specific example again, we have this. Hopefully it isn't too terribly hard to understand. In this case, angle 3 measures 33 degrees, and every single angle complementary to it must measure 57 degrees. Since they all must measure 57 degrees, they all must be congruent. Now we get to these last two theorems. The first theorem from this section, the vertical angles theorem, will get used a lot. It comes up all the time. The next two theorems will be useful once or twice this year, but that's it. They play a very minor role. But these last two theorems are so minor, it is surprising they even make an appearance in the book. They are not necessary, and there are always other ways you can do a proof instead of using these things. However, they show up in the book, so I'll put them here just to be thorough so you don't feel like you are missing anything. You know theorems aren't very major when they don't even have a proper name. So there's theorem 2-4. All right angles are congruent. That seems pretty obvious, right? Since all right angles measure 90 degrees, of course they are all congruent. About the only good thing about this theorem is it is perfect for a beginner proof. We're going to prove that later on. The next theorem has slightly more to it. However, you have to have two angles both congruent and supplementary. Now that situation does come up a lot, but you just don't ever refer to them as congruent and supplementary. You would say they are right angles already, or that there are perpendicular lines or something. You just never ever would be talking about them as two angles that are congruent and supplementary. That's why this isn't a very useful theorem. If the angles are supplementary, then they have to add up to 180 degrees. Since they're the same size, the only measure they can possibly have is 90 degrees. Thus they must be right angles. Just like theorem 2-4, the best thing about this theorem is that it makes a good beginner proof for you to do.